よろしくお願いします。
はい、どうも。Thank you for the introduction. Okay, so I'm going to talk about generic setwise large cardinals. Okay, so first let me explain the background of today's talk. Okay, oops. Okay, so as you know, many large cardinals can be characterized by the existence of elementary embeddings. Okay, so and generic large cardinals. Okay, it's defined by the existence of generic elementary embedding, which means an elementary embedding which is living in some generic extension. So they may not be in the ground model. Okay, so this would be a typical definition. A cardinal kappa is said to be generically measurable if there is a poset P such that in the generic extension VP, we can find a transitive class, N, and an elementary embedding J from V, the ground model B to M, with critical point kappa. Okay, so point is just this M and elementary embedding J may not be definable, or may not be in the ground model B. Okay, so in the last, so in the talk in the last night in Japan, so Fuchino-san also introduced generic labor superhuge. Okay, so it is also a very good example of generic large cardinals. Okay, so what is our advantage of generic large cardinals? So of course, large cardinals is large, very, very large. But unlike usual large cardinals, so generic large cardinals can be small. Okay, so for instance, if kappa is measurable and delta less than kappa is regular, then call delta less than kappa. This is a standard forcing notion. Delta, which is standard forcing notion, it's delta close and forces that kappa equal delta plus. Okay, so this collapsing force is that kappa is generically measurable. Okay, so in particular, so omega 1 can be generically measurable. And so another example is a generically labor superhuge. So a continuum can be a continuum. I have no idea. Continuum is small or large or anyway. So continuum can be generically large, generically labor superhuge. Okay. Okay. So generic large cardinals can be small, but its consistency strength is not small and not weak in general. For instance, generically measurable is consistent with measurable. And I guess so. Fuchino-san's generically labor superhuge for CCC, its consistency strength is very, very strong. Maybe greater, maybe close to super compact or above. Or yeah. Okay, so anyway. Okay, so and usually so elementary, so in the context of large cardinals, elementary source the source model of elementary embedding is a V. It's a proper class. Okay, so however, so the source model of an elementary embedding can be arbitrarily large set in many cases. For instance, this is a very easy observation. Cardinal kappa is super compact if and only if it's setwise super compact. It means for every regular lambda, we can find a transitive set N, which is closed under lambda sequence. And elementary embedding J from H lambda to N with critical point kappa and J of kappa is greater than lambda. Okay, so other large cardinals such as strongly compact, measurable, and strong, and many other large cardinals can be defined by this way. Okay, so among these facts, Nielsen and Schlicht. Schlicht is here? No. Okay, no. Okay, so Nielsen and Schlicht introduced a restricted version, restricted generic large cardinals. Okay, so what is that? The source model of a generic elementary embedding is a set living in B. Okay, so here is one of our generic setwise large cardinals introduced by them. Okay, a cardinal kappa is said to be generically setwise supercompact. If for every regular lambda, there is a poset P such that in the generic extension, okay, there is a transitive set N, which under elementary embedding from H lambda of B to N with critical point kappa, and J kappa is greater than lambda, and N is closed under lambda sequence. Okay, so as generic large cardinals, so this elementary mimic J and N may not be in B, a grand model. Okay, so they also introduced setwise generic version of setwise extendable. Okay, regards that uncountable cardinal kappa is extendable if for every alpha greater than kappa, there are beta and elementary embedding from J from V alpha to V beta with critical point kappa, and J kappa is bigger than alpha. Yes, of course, extendable cardinal is originally setwise large cardinals. Okay, so we can define setwise generically setwise extendable in the natural way. Cardinal kappa is generically extendable if for every alpha there is a poset P such that in the generic extension VP or there are beta and elementary embedding from elementary embedding J from B alpha to B beta in the generic extension with critical point kappa and J kappa is greater than alpha. Okay, so this is
excuse me. Excuse me. So this definition is maybe due to Vananen and Ikegami or someone else. Just for historical. Thanks.
Okay, thank you. Okay, so this is anyway, so this is one of the application of generically extendable. Okay, so extendable cardinals, it is known that extendable cardinals can be characterized by the compactness number of second order infinitary logic. This is the result by Magida. And so Ikegami and Vananen introduced the Boolean second order logic, which is a variant of second order logic between standard first order and standard second order. And the compactness number of Boolean second order logic equals to the first generically extendable cardinal. This is one of the applications of generically extendable. Okay, so trivially extendable, every extendable cardinal is generically extendable via the trivial forcing. Okay, of course, every supercompact is generically setwise supercompact. Okay, so extendables and supercompact have very strong consistency strengths. Okay, however, what this generical version of extendable and supercompact? The consistency strength of those generic large cardinals is not so strong because, okay, so suppose they are proper class many Udin. then every regular uncountable cardinal is generically extendable. Okay, so via the stationary, within the stationary tau forcing. Okay, so this means that extendable and super compact cardinal have very strong consistency strengths, but okay, the consistency strength of generic version of these cardinals is weaker, not so strong, weaker than the proper class of within cardinals. Okay, so this observation also shows that generic extendable cardinals does not imply any large cardinal property such as stationary deflection and failure of square or SCH or some and so on. Okay, so anyway. Okay, so the consistency strength of these cardinals, upper bound of the consistency strength, this is a proper class within. But so a natural question is, what are the exact consistency strengths of generically setwise super compact and generically extendable? How strong or how weak? Okay, so this is a main result. This is one of the main results of today's talk. Okay, the consistency strength of generically extendable cardinal is very, very weak. Actually, so the statement that omega 1 is generically extendable. This is equiconsistent with some weak large cardinal action. Okay, it's very weak because it coexists with V equal L and it's implied by 0 sharp. Okay, so then what is some weak large cardinal action? Okay, in order to explain, let me introduce another generic large cardinals. It is called virtual large cardinals. Okay, so virtual large cardinals were introduced by Zittman and Schindler. Okay, so virtual large cardinals. It's a variant of generic large cardinals, but both source model and target models are set living in V. Okay, so for instance, okay, a cardinal kappa is virtually extendable if for every alpha larger than kappa, there are beta larger than alpha, and poset P such that in the generic extension, we can find the elementary embedding J from B alpha to B beta with critical point of kappa. Not just so, B alpha and B beta are set living in V. But so this elementary embedding is aided by some forcing. So J may not be in B. Okay, so Zittman Schindler shows that this partially extendable cardinals consistency strength of partially extendable is very weak. Okay, so they show if 0 sharp exists, then every silver indiscernible is partially extendable in L. Okay, so this means that every uncountable cardinal is partially extendable in L. And they also showed that the partially extendable cardinal is a downward absolute cardinal. If kappa is partially extendable, then so is in L. Okay, so let me present Zittman and Schindler's argument because it is very interesting, and I'll use their argument later. Okay, here is the point of their argument. Let M be any inner model of ZFC, and X and Y be transitive set in M. Okay, and let J is an elementary embedding from X to Y. But we don't require, but this J may not be in M. Okay, so and the critical point of J is delta. And fix a finite set, a finite subset A of X. Then the forcing called X and this is a standard forcing notion. This is a standard forcing notion. It's a collapsing X to be countable. Then this collapsing over M forces that there is an elementary embedding I from X to Y with critical point delta and Ix and Jx. Ix equals Jx for every X from A. Okay, so this is a sketch of their proof. Okay, so first take a generic G, and in MG fix an enumeration xn of large X. Then define the tree T as follows. Let T be the set of all finite partial elementary embedding I from X to Y, such that its critical point is delta. And domain I is the initial segment of the enumeration. And I and J has the same value on A cap domain I. Of course, T with the initial segment and the extension relation forms a tree. And of course, T is an element of M of J. Now, okay, so this J, so this elementary embedding J. J may not be in MG. J is in VG, but may not be in MG. But okay, this J generates a final branch of T. Okay, this means so T is ill-founded in VG. And by the absoluteness of the ill-foundedness. Okay, T is also ill-founded in MG. So in MG, we can find a cofinal branch F. And so this cofinal branch F canonically generates required elementary embedding this I. Okay. Okay, so this is the explicit exact statement of my research. If kappa is generically extendable, then kappa is virtually extendable in L. But this is follows from a standard argument. And for the converse, if kappa is virtually extendable, then call omega less than kappa. This is a forcing notion. This forces that kappa equal omega 1. And this collapsing also forces that kappa is generically extendable. Okay, so the virtually extendibles, generically extendibles, omega 1 is generically extendable. These cardinals have the same consistency strength. And this is implied by zero sharp. And so of course, converse does not. Okay, so the proof of 1 is straightforward, so I'd like to skip. Okay, for 2. Okay, first take a generic G and fix a large alpha. Okay, by Gitman-Schindler theorem. Okay, so this collapsing forces since kappa is assumed to be virtually extended. This big collapsing forces that there is an elementary embedding J from V alpha to V beta for some beta. And J kappa is greater than alpha. Okay, so next take a V called omega less than J kappa generic H, which extends G. Okay, so now in VH, okay. So in VH, we can find the elementary embedding J from V alpha to V beta. And so by the standard way, J can be extended to J from V alpha G to V beta H. by the standard lifting argument. Now, okay, so since alpha is sufficiently larger than kappa, B alpha G, this is a generic extension of B alpha, but this is the same to VG alpha. So the initial segment of VG. And similarly, V beta H, this is the initial forcing extension of V beta by H, but and this is the same to VH beta. Okay, so this means J is an elementary embedding from VG alpha to VGH beta. Okay, so in VAG, so in VG, so this collapsing force is that J is an elementary embedding from VG alpha to VGH beta. Okay, so this means that kappa is generically extendable in V equal omega in VG. Okay. Okay, so and or generic setwise large cardinals have some interesting properties. So it is indestructible. Okay, so Leiber shows that after some preparation forcing, supercompact cardinal kappa is indestructible under any less than kappa directed cross forcing. To contrast with this, is Leiber's theorem. So Bagarian, Hamkins, and Sapronis and me shows that if kappa is extendable, so kappa is never indestructible. This means if kappa is extendable, then every non-trivial less than kappa cross forcing must destroy the extendability of kappa. Okay. However, on the other hand, generic extendability and generic setwise supercompact is always indestructible by certain forcing notion without any preparation. For instance, every kappa CC forcing preserves generic extendability and generic setwise supercompactness of kappa. Moreover, if kappa is omega 1, then every proper forcing preserves the generic extendability and generic supercompactness. Okay, so yeah. Okay, so but I'd like to make this remark. As I said, if there are proper class many Udin, then every regular uncountable cardinal is generically extendable. Okay, but this means that under proper class many Udin, okay, if kappa is a regular uncountable and P is a poset which preserves the regularity of kappa, then P also preserves the generic extendability of kappa. So point is that P, so we don't require P has a kappa CC or kappa closed or something. So only requires P preserves the regularity of kappa. So under this situation, okay, so generic extendability is preserved by any reasonable forcing. Okay, so the Nielsen, Schlicht, and me asked. Okay, sorry, yeah. Even if kappa is greater than omega 1, it's the generic extendability of kappa preserved by kappa directed forcing like Leiber indestructibility. And as far as we have no consistent example that generic extendability of kappa can be destroyed by some poset which preserves the regularity of kappa. I don't know a consistent example. Yes, the problem is here. Okay, so proper class many implies so generic extendability indestructible by poset which preserves the regularity. So if you want to get counter examples, we start from some special model, so which has no proper class Udin or something. It is a hard point of this question. Okay, so Okay, so now as we see, generic setwise large cardinal property of omega 1 as a special place. So consistency is very weak and it's always destructed by certain forcing. Okay, so the question is, how about such a generic setwise large cardinals greater than omega 1? Okay, in particular, Nielsen and Schlicht asked, does the existence of generic setwise supercompact cardinal greater than omega 1 imply zero sharp or not? Okay, so here is a partial answer. If there is a generically setwise supercompact cardinal strictly greater than omega 2, then zero sharp exists. Okay. Oh. Okay. So this fact. Okay. So this then follows from this lemma, but this may be a kind of folklore. Okay. Here, suppose there is an elementary embedding from J from L alpha to L beta with critical point delta. If the critical point delta is greater than omega 2 and alpha is greater than delta plus in L, then zero sharp exists. Okay, so this follows from a standard condensation. Okay, so this follows from a standard condensation argument and Jensen's covering lemma. Okay, so I'd like to skip this. Anyway, so this lemma proves this lemma proves this. If there is a generically setwise supercompact cardinal strictly greater than omega 2, then zero sharp exists. Why? Okay, now fix a large lambda and fix a poset P, which forces that there are transitive n and elementary embedding from J from H lambda B to n with critical point greater than omega 2B. And n is closer than the lambda sequence. Okay, so in the generic extension, this elementary embedding J has critical point greater than omega 2V. So we have omega 1V is equal to J of omega 1V. And so of course this is a omega 1 in N. But because N has a closure property, so omega 1 N is equal to omega 1 in the generic extension. Okay, similarly, omega 2V is the same to omega 2 in the generic extension. Okay, so omega 1 and omega 2 are preserved by this forcing. Okay, so J restricted to L lambda. This is it is an elementary embedding from L lambda to L beta for some beta. Okay, so we get the elementary embedding from L lambda to L beta, and critical point of J is greater than real omega 2. Okay, so by the previous lemma, by this lemma, we have that zero sharp. Actually, we can get more by the covering lemma of Dotto-Jensen core model. So we can prove that generically setwise supercompact cardinal strictly greater than omega 2. Its consistency strength. So its consistency means the consistency of measurable cardinals. Okay, so now I have no exact answer to this question. What is the exact consistency strength of the generic extendability or generic supercompactness of a cardinal greater than omega 2? As I said, upper bound is a proper class of Udin. Lower is a measure. There is a huge gap. If you know deep inner model theory, you can get more, and you can increase the lower bound of this. I think a lower bound maybe many within 1 strong or something. Okay, so Okay, so anyway, so consistency strength of a generic setwise large cardinal strictly greater than omega 2 is strong, but omega 1 is not. So the rest problem is what about omega 2? What is the consistency strength of generic extendability and generic supercompactness omega 2? I have no answer. But okay, this is a very restricted partial answer. Okay, so this shows that okay, so suppose GCH and kappa is virtually extendable. Then there is a forcing extension VP in which kappa equal omega 2 and this P preserves omega 1. And in the generic extension, omega 2 is a kind of less than alpha, generically less than alpha omega 1 extendable. This means for every regular lambda less than alpha omega 1, there is a poset Q which forces that there are regular theta and elementary embedding J from H lambda VP to H theta VPQ with critical point kappa. Okay, so okay, this is a sketch of the proof. Okay, so we use the Yensen's poset P. Okay, P has what is this poset? P has a kappa CC. P forces kappa equal omega 2, and P preserves omega 1 and okay, so P also forces that every regular cardinal lambda in B between omega 1 and kappa has cofinality omega in the generic extension. So this is a generalization of number forcing. Okay, so then fix a regular lambda less than kappa plus omega 1. So in this collapsing V equal lambda, okay, because kappa is virtually extendable, so there is an elementary embedding J from H lambda B to H theta B with critical point kappa. And because P has a kappa CC, we can check that P is a complete suborder of J of P. Okay, so now take V equal lambda JP generic H. And let G be the J inverse image of H. Okay, so by the chain condition, this G is JVP generic. And so this elementary embedding J can be extended to J from H lambda VG to H theta VH. Okay, so note that this J, so this J may not be in VH. Okay, so on the other hand, in VH, the cofinality of lambda is omega. And here is a point, since lambda is small, small means lambda is less than kappa plus omega 1. In VH, we can find a countable family Xn such that each Xn belongs to VG. And the VG cardinality of Xn is at most omega 1. And the union of Xn is equal to H lambda VG. Okay, as I said, so this J may not in VH, but we can check so J restrict to Xn is in VH. Okay, so now we can use a variant of Zittman-Schindler's theorem. So in VH, consider the tree of all partial elementary embedding from some Xn to H theta VH. It forms a tree of height omega 1, and so this J witnesses that T is well founded. Sorry, T is ill-founded. Okay, so in VH, so that 3T also well founded, and we can find an element. We can find the elementary embedding I from H lambda BG to H theta VH with critical point kappa. Okay, so why we assume that lambda is kappa plus omega 1? The reason why is here. If lambda is small, we can take such a family Xn's by easy induction. Okay, so I'd like to ask this question. Does the Jensen's poset force is the following for every regular lambda in B between omega 1 and kappa? There is a family Xn, a countable family Xn such that each Xn is in B and its cardinality, V cardinality is at most omega 1 and the union of Xn is lambda. It's okay if lambda is less than Aleph omega 1. This follows from easy induction. But I wasn't able to go through Aleph omega 1. And if the answer to this question is yes, then we can prove that omega 2 is generically extendable, is equiconsistent with equiconsistent with my partially extendibles. Problem is that I don't know how to construct this Jensen's poset. I only know it's a very, very complicated poset. It's a kind of a device to countable support iteration subcomplete or L forcing or something. I am not sure. Okay, so if you know this Jensen's poset and you have this question, please tell me. Please tell me now or later. Okay, so okay. Okay, so okay, next let's compare generically supercompact and generically extendibles. Okay, the standard every extendable cardinal is a limit of supercompact cardinals. This means that the consistency strength of extendable cardinal is much stronger than supercompact. Then the question is, how about generic extendable and generic supercompact? Okay, so answer is okay. There is no gap. These have the same consistency strength. Namely, if kappa is generically setwise supercompact, then kappa is virtually extendable in L. Okay, so this theorem means the consistency of generically setwise supercompact is the same to consistency of generically extendable. Okay, so to prove this, we need more large cardinals. Okay, so it's called jointly large cardinals. Okay, so Sapronis shows that extendable cardinals can be characterized by jointly large cardinals. He shows that kappa is extendable if and only it's jointly super compact and super strong. What is that? For every alpha less greater than kappa, there is an elementary embedding J from V to M. Such that this J witnesses both super compactness and super strongness. Okay, so critical point of J is kappa and J kappa is large and M is close than the alpha sequence and Vj of kappa is contained in M. Okay, so actually, by a similar argument, we can show virtual version of the Sapronis cell. Kappa is virtually extendable if and only if it's virtually jointly setwise super compact and super strong. This means for every alpha, there is a transitive set N and poset P such that in the generic extension bar, there is an elementary embedding J from V alpha to N, a critical point kappa. J kappa is greater than alpha and N is close than the alpha sequence in P, and M contains Vj kappa. Moreover, we can check that this closure property is not necessary. Actually, this is virtually extendable is equivalent to virtually jointly setwise strong and super strong. Oh, it's too long name. Oh. Okay, so anyway. Okay, so this is a okay, so this is a sketch of the proof of this. Okay, so suppose kappa is generically setwise super compact. Okay, we shall see that kappa is virtually jointly setwise super compact and super strong in L. Okay, so if kappa is greater than omega 2, then it's okay because zero sharp exists. Okay. So we may assume that kappa is less or equal to omega 2. In this case, kappa must be a successor cardinal. So say kappa equal mu plus. So mu is omega 0, omega or omega 1. Okay, so fix a large alpha and take a poset P such that in the generic extension, we can find the transitive set N, which is closed and alpha sequence and elementary between J from B alpha to N. Okay, so J restricts to B alpha in L. This is an elementary embedding from V alpha L to N cap L. But by the condensation, N cap L is an element of L. And this of the form L beta for some beta. And because N is closed under the N is closed in the generic extension. N cap L is also closed under alpha sequence in L. Okay, so now J of kappa class. Consider J of kappa. J of kappa is equal to J of mu plus, of course. But by the closure property of N in the generic extension, J of mu plus is the same to mu plus in the generic extension. Okay, so this means J of kappa is a regular cardinal in the generic extension. Okay, so using this fact, we can check that J kappa is in fact inaccessible in L. Okay, so this means that Vj kappa of L, this is just L of J of kappa. And of course, this is contained in N cap L. Okay. Okay, then we can apply JIT machine Russell. Okay, so the forcing with some large collapsing over L. This collapsing is such an elementary embedding. So, okay, so in L, so some in L, so this means in L, kappa is virtually jointly setwise super compact and super strong. Okay, this is a proof. Yeah, sorry. Okay. Okay, so we proved that generically extendable is consistent with virtually extendable. So next question is, how about virtual super compact and generic super compact? Okay, so let us consider the virtual version of setwise super compact. Okay, so cardinal kappa is virtually setwise super compact. If for every regular lambda, there are transitive set and poset P such that N is closed under lambda sequence, and in some generic extension, we can find the elementary embedding from H lambda B to N with critical point kappa and J kappa is greater than lambda. Okay, so this now. Okay, so so here is a remark. So you may ask what is you may want sorry. The condition J double hook lambda is in N. So you may want to add this condition to or virtual setwise super compactness, but it's too strong. It's a too strong requirement because equals about the definition. If we add this condition to the definition of this virtual supercompact, then it's equivalent to the usual supercompact cardinal. It's too strong and it's out of our scope. Okay, so but here is one natural definition of virtual supercompactness. But here is another definition. Magido shows kappa is supercompact if and only for every alpha greater than kappa, there is beta less than kappa, and an elementary embedding J from V beta to V alpha, with J of critical point of J is kappa. Okay, so this is an this is just a setwise definition of supercompactness. Another setwise definition of supercompactness. So this characterization led us to this another virtual supercompactness. Okay, so kappa is virtually M supercompact if for every alpha greater than kappa, there are beta less than kappa, and there is poset to be such that in the generic extension, there is an elementary embedding J from V beta to V alpha with J of critical point of J is kappa. But yes, okay, so Dittmann-Schindler shows that these are equivalent definition. In fact, kappa is virtually setwise supercompact. If and only kappa is virtually M supercompact. In fact, Dittmann-Schindler proved more. Okay, so this is a virtual strong cardinal. Kappa is virtually setwise strong if for every alpha greater than kappa there are transitive set N and poset P such that V alpha N contains V alpha, and in the generic extension we can find a certain elementary embedding. Certain elementary embedding with critical point kappa, and J kappa is bigger than alpha. Okay, so this virtual strong is equivalent to virtually setwise supercompactness. This is somewhat strange. Okay, more surprisingly, Nielsen shows that in fact virtual supercompactness is equiconsistent with virtual setwise measure up. It looks more weaker. So okay, this is very surprising. Okay, then compare. So let's compare generic supercompact and virtual supercompact. Okay, so this lemma is easy. So if kappa is generically setwise, generically supercompact, then kappa is virtually supercompact in L. Okay, this follows from a straightforward argument. And so this is also standard. This follows also from a standard argument. If kappa is virtually extended, then V kappa is a model of GFC plus their proper class many virtually setwise superconductor particles. However, we already showed that if kappa is generically setwise supercompact, then it's virtually extendable in L. Okay, so we get this using these facts, using this theorem, we can get this. If kappa is generically supercompact, then L kappa is a model of GFC plus their proper class many virtually setwise supercompact cardinals. This means that consistency of generically setwise supercompact. This is much stronger than virtually setwise supercompact, unlike extendable generic and virtual extendables. Okay, so 10 minutes. Okay, now. Okay, so let's turn to another large cardinals. Okay, so this it is called the tall cardinal. which was introduced by Harmkins. Okay, so cardinal kappa is tall if for every alpha there are transitive class n, which is closed under kappa sequence and an elementary j from V to n with critical point kappa and kappa. Oops, sorry. Okay, sorry. Alpha, j of kappa is greater than alpha. Okay. Now, so the virtual and generic tall should be defined as follows. Well, kappa is virtually setwise tall. If for every regular, okay, we can there is a transitive set which is closed under kappa sequence, and there is a poset of P, such that in the generic extension, we can find the elementary embedding from H lambda to n critical point kappa, and j of kappa is bigger than lambda. And so we define generically setwise tall. We define generically setwise tall if for every lambda, and we can find poset of P, which forces in the generic extension there is a transitive set which is closed and which has a closure property and elementary embedding from H lambda B to n. Okay. Now, okay, so we showed that if J is a generically setwise supercompact above omega 2, then zero sharp exists. By the same argument, if J is a generically setwise tall greater than omega 2, then zero sharp exists. And moreover, by this definition here, if kappa is successor, then kappa is generically setwise tall. If and only if it's generically setwise supercompact. Okay, so this means that consistency of generically setwise supercompact is the same to generically setwise tall. Okay, so now tall cardinal. So the definition of tall cardinal is similar to strong cardinals. But tall is not equivalent to strong in general. However, Harmkins shows that consistency of tall cardinals and strong cardinals, these cardinals have the same consistency strength. So the natural question is, what about virtual and generic strong, tall and strong? How much is the consistency strength of these generic and virtual cardinals? Okay, here. Okay, now this is easy. Yes, first, every virtually setwise strong cardinal. As I said, virtually setwise strong is equivalent to virtually setwise supercompact. And obviously, virtually supercompact is virtually setwise tall. So every virtually strong is virtually tall. And virtually tall is downward absolute to L. Kappa is L. And in L, it is not hard to check. So in L, every virtually tall is virtually strong. This means that virtually strong and virtually tall, these have the same consistency strength. Okay, like this. Here and here. Okay, so but I'm not sure. So in L, virtually tall and virtually strong, these are equivalent, but I'm not sure it's always equivalent or not. Okay. Okay, so finally let's compare generic strong and generic tall. Okay, so we have to define what is generically strong. Okay, the definition should be as follows. Kappa is generically setwise strong. If for every alpha, we can find a poset of P such that in the generic extension, there is a transitive set N which contains V alpha of the generic extension. And there's an elementary embedding J from B alpha to N with critical point kappa and alpha. J kappa is greater than alpha. Okay, so but the situation is similar. If there is a generically setwise strong greater than omega 2, then 0 sharp exists. And if kappa is generically setwise strong, then in fact kappa is virtually jointly setwise strong and super strong in L. Okay, so as I said, so virtually extendibles equivalent to virtually jointly setwise strong and super strong. So okay, so as a conclusion, so generically setwise tall, generically setwise strong, generically setwise super compact. These have the same consistency strength. Okay, so this diagram is today's conclusion. Okay, so generically setwise super compact greater than omega 2. The consistency strength of this is strong, as implying 0 sharp. But the compass direction is not. And 0 sharp implies the consistency of virtually extendibles. And so virtually extendibles is consistent with generically extendibles, generically super compact, generically tall, and generically strong. Okay, so the consistency of these means a virtual super compact, virtual tall, virtual strong, and these have the same consistency strength. And so the generic version, the consistency of generic version is much stronger than virtual one. However, so extendable and generic extendable and virtual extendable. Only extendable has the same consistency strength. I'm not sure why. Okay, so it's a good time to finish. Okay, so here's a reference. Okay, so finally, so this is a workshop on the occasion of Sakai Fujino's retirement. So I'd like to say Fujino-san. Okay, so thank you very much for your great contribution to logic and set theory, and so many help and support to me and us. Okay, as you said, so retirement does not mean retirement from mathematics. Does not mean retirement from mathematics. Yes. So you will have retirement from many office work. So you will have many time for mathematics. So you can do mathematics more and more. So please enjoy it.
Yeah, thank you very much. Adrian Matthias noticed that you get more work when you retire. So I
yes, right.
What happens to me, but okay, thank you very much.
Okay, so that's all. That's all. Thank you so much.
Okay, thank you, Toshimichi. Thanks for your nice talk. And do we have any questions or comments? Sakai, yes.
Yep. Sorry, so Fujino-san, mic.
We don't hear you.
You are muting. Sakai, you are muting.
Sorry. So I don't have yet a good overview of your great results. So my question might be a little bit out of context, but is it? Can you also consider naive generic version of all these things? Does it have meaning?
Yes. So maybe we can define generically setwise huge or generically setwise super huge or something. Okay, so maybe yes, but there are some problems. The first problem is how to define.
Yeah. Okay. Yes. Okay.
Yes.
Of course, there's this problem.
So there are some options. So
yeah. Right. Yeah.
yes, so
And
maybe.
Yeah.
Okay, so maybe so. Maybe candidate for any alpha for any alpha less than kappa, or there is poset p, and so which force is about exist n and exist j map v alpha to n and less j kappa n is n. Okay, and so maybe so. This is the first candidate. Okay.
Yeah.
But this is not so strong because this follows from genic extendability. Okay, so another candidate maybe so for every alpha, there is some beta greater than alpha, there is some p, which forces exist n and exist jv beta to n. Okay, so n is close under j of kappa sequence. Okay, alpha greater than j of kappa, and so okay, maybe so. Alpha greater than j of kappa beta. This is another candidate. But maybe so. Okay, so yes, of course this follows from zero sharp, but okay, I think so. Consistency of this is larger than genic extendability. This is my but this is just my guessing. I haven't checked yet.
Yeah, thank you. Yeah.
Okay, Joan has a question, I think.
Well, yeah, just hi.
Yeah.
Thank you for the talk. Very interesting. Let me just turn the video on. Okay, there we go. Thank you for the talk. It was very interesting. I was wondering if you have looked also at the CN versions of these virtual extendable cardinals, like in the ones that are studied in the Gidman-Schindler paper, and also in my paper with Vika and Ralph, where we studied the n virtually n remarkable or generic n remarkable.
Yeah. But so remarkable. So what is the definition of generically remarkable?
Well, I mean, that's the generalization of remarkability, in which you look at the virtual, you look at the generic version of it, and you require that the image of the critical point is in Cn. Yes, it's a cardinal that is sigma n correct.
I see.
I mean, this forms a hierarchy, strict hierarchy, but I don't know in terms of in your general setting of computing the consistency strength of all these cardinals. I was wondering where these cardinals fit in, and what is the relative consistency strength compared to the cardinals, the setwise generic super compacts, or setwise tall or setwise strong. I mean, where do they fit in this classification, or in this hierarchy? Anyway, I don't know. I'm just asking because I was wondering if you have looked at this as well, or you haven't.
I have no idea.
It would be interesting to know if they actually form a finer hierarchy, or anyway.
Maybe these so remarkable cardinals around here. I have no idea. I have no idea. Sorry, I have no idea.
Okay. Thank you.
The remarkables are this equivalences with virtually setwise.
Yeah. With virtual, they are they're essentially the same as virtually extendable or n virtually or Cn virtually extendable. Yes.
Yeah.
Okay, I think Philip has a question.
So Asaf Karavita. Oh, sorry.
Hi, Toshimichi. That's a great talk. It was really nice. No, it's just a comment.
Yeah.
I mean, I think you asked about whether the prospect of having, I can't remember now the adjectives. I mean, the virtually generically super compact above omega 2, and you had this covering lemma using the Dodd-Jensen covering lemma. I mean, I think that property looks like you probably go beyond a strong cardinal, which you're asking about. I think it'd probably go up to a Woodin cardinal. I'd hesitate to say anything more because my kind of knowledge gives out. But,
just wait. Well, okay.
But it looked to me.
Yeah. Okay. So this one, yeah.
Yes.
Okay.
Yes.
Okay.
Yeah.
So
this property here, right?
Yeah. Okay. So we can get a consistency of strong or something, right?
Yes. Elementary embedding form.
Yeah.
Yes, I think up to, yeah, I would hesitate to say anything beyond a Woodin cardinal. But,
really? It's unexpected. It's unexpected.
You didn't think it would go up that far? Yeah, I mean, you've got. I mean, normally these arguments, they work by extending and embedding from a little piece of L to all of L.
Yeah.
So I was thinking if you had K, for example, below a Woodin cardinal, you've got enough closure there to perhaps extend the embedding from that piece of K to all of K. But yeah, it's true. I shouldn't say too much. Perhaps that would need to be thought about a bit.
Thank you so much. Yeah.
But yeah, that looks promising. Okay, that was all. Thank you.
Yeah, thank you.
Okay, any other questions, comments?
I think Asaf posted a question or comment in the chat.
So Philip Wedge just answered the question. It was the same question. Actually.
But it's just okay. Okay. Very good.
Yeah.
Yes. I have to go on. Okay. Okay. Perfect.
Okay. Any other questions, comments? I think it's not the case. So let me finish this. Well, let's thank Toshimichi again for his talk.